Sure.
Okay,
I'm ready.
so it gives me a great pleasure to introduce Rob Myers, who's the director of Perimeter Institute and my old postdoc mentor. And we are very happy that he's managed to find time from his busy schedule and tell us about quantum extremal islands made easy.
Okay. So I should start by acknowledging that I have some very smart collaborators. There's some students and a postdoc here. Well, the students, Vincent Chen, Josh Sandor at Perimeter, Dom Newmanfeld is a postdoc here, and Ignacio Reyes is a postdoc actually in the AEI in Potsdam. And we put a paper out in June, and there's another paper that I hope comes out this month, not too long from now. In any event, come on, there you go. If you've ever seen me give a talk in the past decade, you know that this is one of my favorite all-time slides about holographic entanglement entropy. And that's really been a interesting forum for ADS-CFT, where we've learned new things about quantum field theories, strongly coupled quantum field theories, but we've also, the learning has gone the other way. We've learned about, features of quantum gravity. And so what I'll be telling you about today is how this tool is teaching us some new things about the information paradox. So Prem already talked about, well, he gave a very nice talk yesterday and talked about this issue. And so basically this was a discovery that goes back almost 50 years to Stephen Hawking. And what he discovered was that black holes are not entirely black, but when I take into account quantum effects, they actually radiate. And they radiate what looks like thermal radiation. And that led to a paradox, because I can start here with, well, this is a Penrose diagram of a black hole that, or a system that collapses to form a black hole. The black hole emits Hawking radiation, which eventually carries away all of the energy in the black hole and produces a space-time that has a structure like this. And the paradox is that I can start here initially with a pure quantum mechanical state, but eventually up here, where I'm just left with this cloud of Hawking radiation, if the Hawking radiation is really thermal, then in fact, we have a mixed state. And so we violated, well, the basic rules of quantum mechanics, or unitary time evolution. By unitary time evolution, a pure state always evolves to a pure state. And so something strange has happened here in this process. I wanted to talk about it in terms of entropy. And so how do you describe this puzzle in terms of entropy? Well, we can look at the radiation and we can ask how much entropy there is in the radiation. Initially, there's no radiation, and so the entropy is zero, but then more and more radiation comes up and out, and so the entropy builds and builds until eventually the black hole has disappeared. I've got a fixed amount of radiation, and the entropy caps off like this. This is what I described in the previous transparency, but of course, that's not what we would like to see. What we would like to believe is that the system somehow is evolving unitarily. And Don Page was the first to look at that a long time ago. And what he argued was, in that case, the curve should look like this. If somehow the radiation and the black hole always are in a pure state, then the black hole actually puts an upper bound on how much entropy the radiation can have. And so the curve should look somewhat like this. Initially, the radiation cloud grows and the entropy grows with it. But about the halfway point in the evaporation process, it should start to decrease again. And that hints that there should be correlations between the radiation that was emitted at early times and the radiation that's being emitted here at later times. And Prem talked about that a little bit. But this page curve, as it's known, would be a key signature that there's actually unitary time evolution occurring. And so how have we been learning about that from holographic entanglement entropy? Well, was really, there's a lot of excitement now, but it was kicked off last spring by these two papers by Jeff Pennington and another paper by Elmeri, Engelhardt, Marolf, and Maxfield. And then there's another key paper that I'm going to rely on from about a year ago, from last August, with these gentlemen and this woman, where they added an extra feature to this second paper. But let's think about, well, okay, and then I should add, of course, since then there have been, well, now dozens of papers, and the list of contributors is a long one. This is by no means complete. I could probably fill the rest of the screen with the names of people who have contributed in various ways. But what I wanted to do is I wanted to just remind you some of the features in this second paper here, and it's more or less the same system that Prem was talking about. But what we're looking at is a holographic system where the gravity is two-dimensional, and so the boundary theory is actually quantum mechanical, or 1 plus 0 dimensional. So I have these two quantum mechanical systems, one on the left, one on the right. The dual to that is a two-dimensional gravity theory. It's a gravity theory known as JT gravity, but that gravity theory is also coupled to a two-dimensional CFT that wanders around in this space-time. Of course, what I'm doing is I'm actually combining these two quantum mechanical systems in a thermofield double state. And so what's forming here in this geometry is actually a black hole in the JT gravity theory. Just some reminders, JT gravity, it's a very special kind of gravity. If I think about gravity in two dimensions, the usual Einstein-Hilbert term is actually topological. And so if I try and vary this, I don't get any non-trivial equations of motion. This would be trivial. And so what Jacqui and Teitelboim did is they introduced an extra scalar field, the dilaton, which appears here in front of this Einstein-Hilbert term. When I vary the dilaton in this particular case, it says that the Ricci scalar is equal to a constant. In our case, it'll be a negative constant, or there'll be a negative cosmological constant. However, when I vary the Einstein-Hilbert term, I integrate by parts, and I get some interesting equations of motion for the dilaton. And I'll remind you that this theory I can think of as a dimensional reduction coming from some higher dimensional theory, and it's describing the physics in the vicinity of an extremal horizon. Alternatively, it's also arisen in holographic discussions of something known as the SYK model. That's a simple, well, the dual theory is a simple quantum mechanical system of some n fermions, and they're coupled by random couplings. But those couplings are drawn from a particular ensemble, so that, well, the average J squared, or the average coupling for any one of these instances, has a particular form that's given here. The other thing, of course, that I said is that we're not just studying JT gravity, but we've got the gravity theory, and we're going to couple it to a two-dimensional conformal field theory. So there's matter running around in the bulk space-time. I also said that we're preparing our quantum mechanical systems in a thermofield double and producing a black hole in the JT gravity. But I also told you up here that, in fact, the Ricci scalar is a constant, or in fact, for two dimensions, what that means is the geometry is just, locally anyway, two-dimensional anti-de Sitter space. And so that's a fixed constant. But we think of it as a black hole by looking at it in this particular coordinate system, where, in fact, well, this metric function f has a vanishing or it has a 0 so that it looks like there's a horizon. We can think of these, a set of coordinates that'll come up later in higher dimensions is, this is a version of ADS Rindler coordinates. So there's a particular horizon that's just induced by the choice of coordinates. Of course, in this particular setup, that horizon has a special meaning, in fact, and that's because of the dilaton that's also in the background, and it has a solution in this coordinate system that looks like this. But basically what happens is, if I move in from the boundary here, the dilaton is decreasing. If I'm moving in from this side, it's decreasing. And then if I move into the interior of the black hole, it continues to decrease. But it's that special structure of the dilaton field that gives this, well, that really gives meaning to this horizon and the choice of coordinates that I've given here. In any event, that is only actually part of the system. As I've drawn it here, there's this other bit where, in fact, there is no gravity. There is a two-dimensional conformal field theory. In fact, the same conformal field theory wandering around on a half line or on a half plane. And this region is coupled to one of the quantum mechanical systems, and it's called the bath. The bath doesn't mean there's a finite temperature. It just means that here there is a reservoir with a large number of degrees of freedom. And the new thing that these authors do is, usually when we think about a black hole in ADS-CFT, we have reflecting boundary conditions, and so the black hole remains in equilibrium. However, in this particular case, with this coupling, what happens, or what is allowed to happen, is the Hawking radiation can leak out of our holographic system and into this bath system. And that allows the black hole, the holographic black hole here, to evaporate. And by considering holographic entanglement entropy, or by really considering a quantum version of holographic entanglement entropy, what one is able to do is reproduce the page curve, or that's what these folks showed here. So what's going on with these quantum extremal surfaces? Remember, in holographic entanglement entropy, what we do is just extremize the geometry of the surface in the bulk. In this particular case, what that would with JT gravity, what that would correspond to is, well, usually we choose a region in the boundary. Because we have this 1 + 0 dimensions, we actually choose the entire boundary. We can ask, in this particular case, what's the entanglement entropy of the quantum state on, say, a particular time slice here. We need a bulk surface that's homologous to that, so that's just a point in the interior, in the bulk. And what we are instructed to do by Ru Takianagi or by Zhidong is to basically extremize the coefficient of the Einstein-Hilbert term, and that's this dilaton field. And so in this particular black hole that I described before, that extremal point is none other than the bifurcation surface, or it's the middle of the X here, where the past and future horizons meet. However, that's not quite what our friends instructed us to do. Rather, they're following this prescription by these folks here, or it was really championed by Engelhardt and Wall, to think about quantum extremal surfaces. And there we're taking the geometric contribution, or the Wall-Dong entropy of this particular surface, but we're also looking at or considering the quantum corrections to that, or the contributions of the matter fields in the bulk. And to do that, what we do is we consider a partial Cauchy surface going from our candidate quantum extremal surface here out to the boundary slice that we're interested in. And we evaluate the entanglement entropy of the quantum fields on that slice. And I could choose different Cauchy slices here, as I've shown, but because of unitary time evolution of the quantum fields in the bulk, the entropy of the quantum fields is going to be the same, either here or here. On the other hand, if I move the red dot around or I move my candidate surface around, I'm stretching those surfaces out. And so both the geometric term here and the quantum term are going to change. And what we're instructed to do is extremize the combination or the sum of those two. And when we do that, the claim is when we do that properly in this particular system, we reproduce the page curve, so we get some expression like this. And the key feature is, of course, that there's a new saddle point. There's a competing saddle point. And so there's one particular quantum extremal surface that describes this phase where the entropy is growing, but there's another saddle point that describes, or another extremal surface that describes this late time phase where the entropy is decaying away. And so that's a remarkable result.
Question, Rob.
Yeah, sure.
Gautam, go ahead.
Oh, good.
Rob, can I ask you a question?
Sure. Yeah.
So this is regarding this quantum extremal surface description. So here we are including only the one loop contribution, from
Yeah.
So why is that enough? I mean, why shouldn't we, take more stuff, including non-perturbative or something?
Oh, so I'm not here. In principle, you could work harder and you could calculate higher loop contributions. It turns out that the one loop contribution will suffice. In fact, I'll just move ahead, and I'm hoping Gautam heard my answer. But you should ask me to comment on what we're actually doing in the next transparency. And in this next transparency, what I'm doing is I'm just telling you about the embellishment that these folks made to this two-dimensional model. What they said is, well, this calculation here works for any two-dimensional CFT. So let's pick a two-dimensional CFT that's holographic. And in that particular case, what we can do is we can replace this two-dimensional CFT by an ADS3 or by a bulk space-time down here. And similarly, the two-dimensional CFT that lives in this gravitating region over here also induces or is replaced by a dual ADS3 region. Now, the full model, you have to introduce other bells and whistles, like this end of the brane, end of the world brane. But more or less, the thing that this does is it takes this story and it lets me describe it in terms of more or less ordinary holographic entanglement entropy. And so for each of these different phases now, there are RT surfaces down in my ADS3 bulk. And one of the technical advantages in this perspective is that the entropies are now purely geometric, at least from the ADS3 perspective. And so what I'm extremizing is this generalized entropy that I described as having sort of a Bekenstein-Hawking contribution and a quantum field contribution. But in our case, that was really this dilettante term. But all of this is really just the contribution coming from the Ryu-Takeyanagi surface, or the area of the Ryu-Takeyanagi surface. And this now, in fact, is the planar contribution to the entropy of the conformal field theory there. And we're working at far beyond one loop, but we're also working in this large N approximation. And so we know that this is the leading contribution to the entanglement entropy. I don't know if that makes you any happier, or if you have another question at this point.
Yeah, well, thank you. Let me get back to this maybe at the end of the talk again.
Yeah, we can talk more about it at the end. I mean, yeah, let's just do that.
I mean, are you saying that it's getting geometrized when you use this double holography
Yes.
picture? Even the one loop contribution.
Well, the one loop contribution is now hidden in the area of the RT surface down here.
Right.
And so it's just the RT entropy, or the usual holographic entropy. Well, but in fact, you're capturing much more than that. You're capturing all loops in the planar approximation, and you're in a large N approximation where you know that is a large contribution.
I see. Okay, thank you.
So given these two papers, we seem to, for this particular system, reproduce a page curve, but and that's marvelous. It seems to suggest that in JT gravity that the evolution, the evaporation of the black hole is unitary, but it raises lots of questions. You know, how important was it that it was a two-dimensional theory of gravity? Are the degrees of freedom on this Planck brane or this gravitating region, is that really a part of the boundary theory or a part of the bulk theory? Was it important that we were working with JT gravity? There was this ensemble average or averaging over couplings in the SYK model. Was that an important feature? You know, how did the radiation really carry the information out of the black hole? And I can give you well, this is just to indicate there are lots of questions. I can give you some answers here, but these are answers that I'm going to derive from looking at this same system, or actually a new set of systems in higher dimensions from a more holographic perspective. My construction is going to be a more standard construction of ADS-CFT, and all of these new insights, you know, about the page curve are really going to seem, well, I hope by the end of the talk, are going to seem more familiar as properties that we knew about, or arising from properties that we knew about from holographic entanglement entropy. And so this isn't to diminish the accomplishments that were achieved here, but it's really to put all of that discussion in a framework where we have more intuition, and hopefully we can gain some more insight into what's going on. As I said, I want to work in higher dimensions, and to do that, I'm going to use something known as Randall-Sundrum gravity, and so I have to do a quick review. But I also have this note that there's this recent paper in June by these two authors, which are using a very similar system. They have a very different perspective on things, but they're using a very similar approach. So what's our Randall-Sundrum gravity? Well, basically, I'm just taking the usual gravity, say bulk gravity of holography. So I have gravity in d+1 dimensions coupled to a negative cosmological constant. And it's just ordinary Einstein gravity. However, I'm going to couple that to a brane with a certain tension. And this is a tension that's very large. And it's going to cause back reaction on the geometry here. And I'll describe the full geometry in a moment. But what Randall and Sundrum discovered is that in this new geometry, you get an extra mode for the graviton that's localized in the vicinity of the brane. And as a result, it looks like there is Einstein gravity on the brane. Or in particular, if I integrate out, if I integrate out the bulk, oh, yeah, okay. There's a technical point I wanted to add, that you might also want to add an Einstein term on the brane, and you can do that. That's something that I would refer to as DGP, for Diwali Gabadadze Parati gravity. It's something that we go on or we describe in detail in our paper, but for the purpose of today's talk, that's not really going to be relevant at all. So we're just going to work with Randall-Sundrum gravity. And what I was saying is that this new mode induces gravity on the brane. I can integrate out the bulk or integrate out the CFT. And what you find is that there's an induced action on the brane that takes the following form. There's an effective Newton's constant here that's controlled by the bulk Newton's constant and the ADS scale in the bulk. And that's governing the strength of gravity on the brane. And then there's a negative cosmological constant, and that's coming from the back reaction. You can see there's a formula here where I've got the brane tension, Newton's constant, and essentially this is the brane coupling to gravity in the bulk. And it's producing some back reaction that sets this effective cosmological constant or the curvature scale on the brane. And then there are a whole bunch of higher curvature terms when I do this integrating out. And you could work hard and calculate all of those. For today's purposes, I'm not going to describe them in any detail. And that's in part because we're going to do a tuning of the cosmological constant so that this effective or brane curvature scale is very, very large. That means this is small. In particular, it's much smaller than the curvature scale or the inverse curvature scale in the bulk. And the reason I'm doing that, or one of the reasons I'm doing that, is that that means that all of these contributions, the higher curvature contributions, are actually suppressed by the ratio of these two scales relative to the first two terms. And so for all intents purposes, the gravity that we're going to be talking about is just ordinary Einstein gravity in d dimensions, and that's a gravity theory that lives on the brane. Now, I promised to tell you about the geometry, the bulk geometry and the back reaction of the brane. And so one way of dealing with that is by using the Israel junction conditions. And so there, I've just got a series of cartoons. Here's a cross-section of d plus one-dimensional ADS. So that's a time slice, a global time slice. I'm going to take that ADS and I'm going to foliate it. Well, I'm going to put this metric on it. And what this metric is doing is it's got this component here, which is actually ADS in one lower dimension. And so what I'm doing is I'm foliating this geometry by slices that actually have ADS-D, or a d-dimensional ADS. And then what I can do is I cut off the geometry at one of those slices at some special value of rho here, this radial coordinate that runs across the picture. Then I make a second copy of that same geometry and I glue them together on the cutoff surface, or this rho B. There'll be a jump in the extrinsic curvature, and by the Israel junction conditions, that jump is controlled by the tension of the brane. And so this kind of geometry where I've got locally ADS over here, locally ADS over here, and a brane running through the middle, that's the geometry that I'm talking about for the remainder of the talk. The other interesting thing is that you can also determine the position of the brane just by looking at this induced action and solving the gravitational equations of motion. And what you find is, well, the simplest solution here is d-dimensional anti-de Sitter space, and it's got a particular curvature scale. But that curvature scale then in this foliation is set by fixing rho. And what you find is that there's a match between solving the Einstein equations on the brane here and setting the curvature scale that way, or going through the bulk and using the Israel junction conditions. They're equivalent. And that's just saying there's a consistency between these two perspectives, the Randall-Sundrum perspective, where there's gravity on the brane, or the usual bulk perspective where I've got a brane interacting with Einstein gravity. A couple of other points. One is that, this is a nice picture that's giving a faithful or a more faithful representation of the geometry, but I'm going to be lazy and I'm going to draw pictures like this, where I just have a cross-section of ADS and a line running through it. But what you should remember is that there's a lot of extra geometry in the vicinity of this line or in the vicinity of the brane. Another point is that an interesting consistency test is that sometimes we'll have RT surfaces that run across the brane here. And what you'll find is that the leading contribution when the RT surface crosses the brane is an area term that's the area on the brane divided by 4 times the effective Newton's constant that appeared in our induced action. And that's again saying that there's a consistency between the bulk perspective of the physics here and the brane perspective that Randall-Sundrum discovered. So with this new higher dimensional geometry, I actually have 3 descriptions of the system, and that's more or less the 3 layers that we saw in the JT or in the 2-dimensional version. So first there's the purely quantum mechanical system, or where there's no gravity. In that case, what I have is, well, a d-dimensional CFT in global coordinates that lives on a SD -1 cross time. But then there's a conformal defect that runs around the equator here. And so that defect is like my quantum mechanical system. The d-dimensional CFT is like my bath. Now, ordinary ADS CFT tells us that that's equivalent to gravity in d+1 dimensions. But of course, the defect also was introduced or is dual to having a brane that's back reacting on that geometry. And that's like the doubly holographic system. The intermediate, where I just do holography on the quantum mechanical systems, or now the defect, is really the Randall-Sundrum description of that physics, where I replace the defect by a brane or gravity on an ADS-D. And so there's a gravitating region here. That's again a d-dimensional ADS space. And in fact, in the Randall-Sundrum description, well, at low energies anyway, this is an effective description. I've got just Einstein gravity. And in fact, there's a copy or 2 copies of that same boundary CFT. Those degrees of freedom also live on the brane here. And so that gives me then in higher dimensions this sort of 3 levels of holography, or these 3 different pictures of the same physics. And so what we're going to try and do in the same way that we did in 2 dimensions is we're going to try and understand the page curve in terms of this gravity here living in the d-dimensional anti-de Sitter space. And until now, I promised you a page curve for evaporating black holes, but in fact, I'm going to look at something that's much simpler. I'm going to look at, well, it was more or less the system that Prem set up for us yesterday. It involves a thermal equilibrium. And so there, what I'm going to do is I'm gonna step back, because our friends here actually looked at this with the 2-dimensional JT gravity. And what I'm going to do is I'm going to ask, well, how do I set up an interesting equilibrium problem? Well, first of all, we have our an equilibrium, or the Hartle-Hawking state, in an eternal black hole. And one way to think about that is in terms of the Euclidean instanton. And so there I have a Euclidean 2-dimensional black hole. The time is now periodic, and that period is chosen so that the place where there was a horizon is actually just a smooth point on the instanton, or on this Euclidean geometry. I want to couple that to a bath, a 2-dimensional bath. And so, well, when I'm doing quantum field theory, I know that A thermal system is described by putting the quantum field theory on a thermal, again, a Euclidean geometry, but the Euclidean time is periodic. And to have these two systems be in equilibrium, we choose the periodicity on this cylinder to match the periodicity in my two-dimensional Euclidean black hole. And so I'm really just preparing the Hartle-Hawking state for this system of black hole coupled to bath. This is a Euclidean geometry. It's a closed Euclidean geometry, but I can think of it as, well, what I can do is I can cut it in half, and I can think of it as a Hartle-Hawking instanton that prepares a particular state on this particular time slice that runs halfway through the geometry. If I take that geometry and squash it out in the plane, oops, I went too quickly, squash it out in the plane, I get a picture that looks something like this. Here's my dotted line. I've prepared a Hartle-Hawking state there. And what I can do is I can evolve that forward in Lorentzian time. In the non-gravitating region, I just get flat space. Flat space, which supports here, though, a conformal field theory at a finite temperature. In the gravitating region, I get my ADS2 black hole. And of course, the two-dimensional CFT here is in the appropriate thermal or Hartle-Hawking state as well. And I don't really, given that state, and I understand where it came from, I can just think about the Lorentzian evolution of that state, either forward or backwards. And then the picture looks something like this. This is my eternal black hole. And this is my thermal bath on either side, coupled to both, now both quantum mechanical systems. There's a thermal bath coupled to it. The question you might ask is, well, this is a thermal equilibrium. Why is there an information paradox? Why should there be something that looks like a page curve? And that's because even though it's equilibrium, this gravitating region and non-gravitating baths are continuously exchanging quanta or exchanging radiation. And so, for example, I might have this quantum over here being correlated with this one over here. This one, that quantum wanders off to infinity, so it remains in the bath. But this one actually wanders into the gravitating region and falls into the black hole. And so what I'm doing with this time evolution is I'm increasing the entanglement between the bath and the gravitating region. And similarly, it can go the other way. We can have quanta that climb out of the gravitating region into the bath region. And an exchange like that is also increasing the entanglement between the gravitating region and the non-gravitating region. And so if I thought about the entropy as I've described it, because of this continuous exchange, I would think that the entropy, in fact, just grows and grows and grows as this flux of radiation is crossing those boundaries. However, the black hole, if I think of it as a quantum mechanical system, it can only store a finite amount of information. And so in some sense, that radiation or that entropy can grow until it hits a maximum. At that point, the register is sort of full, and we start to recycle the quanta, and the entanglement entropy remains the same, or it's capped off. And so this is the kind of page curve that we're going to be talking about. It's the kind of page curve that appeared in Prem's talk yesterday. And we can go through the same kind of discussion of quantum extremal surfaces. And what one finds is that, well, there's two different saddles. In this particular growth phase where the exchange begins and the entropy is growing, there are no quantum extremal surfaces in the gravitating region, and the entropy just grows. In the phase here, what I'm calling the page phase, where the entanglement entropy is capped, I find that there's actually a relevant, or I didn't find, these gentlemen find that there's a relevant quantum extremal surface that appears here in the gravitating region. And so even though I'm calculating the entanglement entropy of these regions here, or the radiation here in the thermal bath, this quantum extremal surface actually provides the minimum of the generalized entropy, or it provides the saddle point with the least action or the least entropy. One of the interesting things here then is, even though I'm calculating the entropy of the bath, the entanglement wedge includes this region here associated with this, these quantum extremal surfaces in the gravitating region. And so that's what's called the quantum extremal island. That's the quantum extremal island of the title. And it also implies that the bath radiation now has information encoded in it about the interior of the black hole. Another surprise at the time was, in fact, that these quantum extremal surfaces actually appeared outside of the horizon of the black hole, which was, well, it's not a contradiction of anything, but it was different than all of the examples that had been seen before, where the quantum extremal surface was near the horizon but inside the horizon. Here it was outside, and we'll have a few words to say about that. So this is a story, though, that what I would like to do now is I'd like to reproduce a story like that, but I'd like to use the higher dimensional system that I talked about before, where I talked about Randall-Sundrum gravity on an ADS brane in d dimensions, or an ADS geometry in d dimensions. So to do that, what we're going to do is we're going to set aside the brane for the moment, and we're just going to think about the empty ADS space over here, d plus 1 dimensional ADS space. And what I'm going to do is I'm going to remind you that that can be described in terms of a black hole geometry, or sometimes it's known as a hyperbolic black hole or a topological black hole, or this is often where the words ADS Rindler come up. And so I'm writing a metric here. GTT has a particular 0 at a certain place, and GR or rho diverges. But this geometry here is just empty ADS space. And so what I'm doing is I'm picking a particular set of coordinates where there's a horizon induced at this rho equals L point. And these are these two orange disks in my cartoon of ADS space. And what that's describing is a thermofield double state. The boundary CFT lives on, well, there's a time direction here, but this is actually a hyperbolic plane or geometry in d minus 1 dimensions. And so it's a thermofield double where the CFT lives on that geometry. And the temperature is tuned to be a very particular temperature, where the R here is the radius of curvature of my hyperbolic geometry. So I've tuned the temperature to match something, a geometric feature in the boundary geometry. But again, this is just empty ADS space. And now what I'm going to do is I'm going to introduce my brane, and I'm just going to stick a brane in the middle of that. So I go like this. Now I've got the same geometry, but I've got a brane in there. Locally on this side, everything looks like as it did before, and on the other side. And so what I've got now, again, is a thermofield double state. I'm coupling the boundary CFT, but it's the boundary CFT with this conformal defect on this particular geometry, and I've tuned the temperature to be like this. And so I've got, I've got a thermofield double state in this new setup, and it looks more or less like the setup that we had before. This is, again, the two-dimensional version. That's the story that I told you about, the eternal black hole coupled to an equilibrium, a bath on either side in equilibrium with it. The higher dimensional version, looks, sorry. Come on. Looks like this. This is now the d-dimensional ADS space that we had before. It inherits the horizon from the ADS Rindler coordinates in the bulk. In the boundary, I now have this geometry R cross the hyperbolic geometry. It's a little bit different than the previous geometry in that here I took flat space, but I actually cut it in half. And so the geometry actually ended on the quantum mechanical system. Here, instead, what I have is I have my conformal defect sitting in the middle of this space, and I'll draw some pictures in a moment. But so what we have is an eternal black hole in the bulk in my ADS, my d-dimensional ADS space, in the gravity theory on the brane, and it's coupled to a bath, now not in flat space, but in this hyperbolic plane cross time. And I'll just picture that here. The Penrose diagram for this geometry is same as the Penrose diagram. It's just a diamond for my, it's the same as flat space. It's just this diamond. But now I've got the defect running down in the middle of that space here. And it has a geometry that is a hyperbolic plane of one less dimension across the time direction. And remember that this stuff lives on the boundary of my ADS space. And so it's living in the diamond on the boundary that lives between the edges of these two orange disks that describe the positions of the horizons. And there's actually two copies. There's my original system and then the thermofield double over here. Now let's think about time evolution in that geometry. This is a t=0 slice. I might pick a region some finite distance away from the defect. And so I might want to ask about the entanglement entropy of the radiation that's absorbed in the bath in these blue regions over here. But I'd want to do that on different time slices. And as time evolves, what happens is that these black edges actually, well, they follow the same kinds of time-like lines that you see in Minkowski space or in the Penrose diagram for Minkowski space, and they all head up towards the tip of this particular Penrose diagram. So in the ADS or in the R cross hyperbolic geometry, these are all a finite fixed distance from the defect. But when I'm looking at it from the global coordinates, these black points are moving closer to one another as they approach the tip of the diamond up there. Now let's look at how that pastes on to the boundary here. Well, I've got one copy of the boundary system, and so I've got my defect up here. I've got the edges of my entanglement region here, and then I've got the blue regions which head off to infinity. But then I do the same thing in the thermofield double, and I get a second copy of that. One of the interesting things is that the two infinities match here at the bifurcation surface, or at the place where the two diamonds, or the two orange discs, the boundaries of the orange disc cross. And so the two infinities actually combine to make a single region, again, when I'm taking this global perspective. And when I think about the time evolution that I drew here, what's happening is I'm stretching those diamonds and I'm bringing them closer and closer to the defect. Now that kind of an evolution on the ADS boundary and thinking about holographic entanglement entropy may be reminiscent of some scenarios that we thought about before. In particular, again, we'll set aside branes. We'll just think about empty ADS space. We think about evaluating holographic entanglement entropy where the region of interest had two disconnected components on either side of the ADS space. then there were always two competing saddles for the RT surface. There were these closed saddles where each region basically ignored the other one, and there was just some RT surface that capped off here and here, and that would be the disconnected phase. Alternatively, there were these connected RT surfaces that stretched from one entangling surface over here to the other one on the other side. And so it depended on the precise size of our region here, but when they were sufficiently small in the appropriate units, the disconnected phase won. But if I extended the size of the region, eventually the connected phase won. And I've actually filled in the RT surface because that's representing the entanglement wedge. And the remarkable thing is that, well, entanglement wedge reconstruction says that the boundary state here encodes information about everything in the bulk that's going on in this pink region here. But in the connected phase, I can actually stretch down and actually, I have information in the boundary theory now about what's happening in the middle of the ADS space. So that's a scenario that may be familiar to some of us from thinking about just ordinary holographic entanglement entropy. And what I'm going to do, though, is I'm just going to do the same thing I did before. I'm going to draw a line down the middle of that picture, and I'm going to now say there's a brane that lives in there. And the same kind of physics is going to go on. The extra geometry, or the brane and the extra geometry of the brane, means that the position or the size where this phase transition changes a little bit, but it's essentially the same physics. And so when the region is relatively small, what I get is this saddle dominating. If I think about the horizon, which runs transverse to the brane, in this case, the RT surfaces are actually stretching across the horizon, and they're joining opposite sides of the black hole. The entanglement entropy grows with time, but the entanglement wedge just tells you about these regions here, close to the boundary. And this is the growth phase of the page curve. When I go to this, well, when I go to late enough times, the regions are big enough, we go to this phase. And now we're in the connected phase. The RT surfaces actually stay on either side of the horizon, but they cut through the black hole. In this phase, because of the way it's set up, the entanglement entropy is actually fixed with time. But now the remarkable thing is that the information in the boundary theory tells about what's going on in the middle of the space, but in particular, it tells us about what's going on in the brane. And this region here, which is a part of the entanglement wedge, but lives on the brane, is precisely the quantum extremal island of the Randall-Sundrum gravity, or from the brane perspective. And so this is the description of the page phase, where the entropy is now capped off. Another interesting way to gain intuition about this, or the words that I've said here, is not to think about the blue regions, but instead to think about the black regions, the complementary regions, for which I get exactly the same RT surfaces. In this case, though, what I'm doing is I'm thinking about the entanglement region entropy of two regions now on either side of the black hole. And this is something that Hartman and Maldacena did. And this kind of description, where at early times the radiation is growing, was described as the thermalization of the entanglement entropy. And then when it capped off here, that was just that we'd reached thermal equilibrium for the entanglement entropy of these two systems. And so that's something, actually, it was described in I think it was the first talk yesterday. But from that perspective, that's, again, a very familiar property or behavior of entanglement entropies when I have a black hole. There was also the question, it turns out that these regions or these boundaries of the quantum extremal island were outside the horizon, or from this perspective, it means that the RT surface did not cross the horizon. But that's something that we can just understand from entanglement wedge nesting. Here, I'm looking at the entanglement entropy of a region that's within the entire half of the boundary. For that entire half, the horizon here is in fact the RT surface. And so this has to lie to one side of the horizon. And that's saying that the boundary of the quantum extremal island, or the quantum extremal surface, appears outside of the horizon on the brane. So, well, that was a lot of words. It went by very quickly. Maybe I should pause and ask if there are any questions. But basically, the story is that we've reproduced this, but we've now reproduced it, or we can reproduce it in higher dimensions, in any number of dimensions. And just for fun, here are some graphs from our upcoming paper where we're drawing this page curve for different dimensions. But I'll just pause there because there were a lot of words. There was a lot that went into that. And I'll just ask if there are any questions about what I was telling you up to now. Okay, well, I took my sip and there were no questions, so I'll just continue on. That's very nice that we reproduced some stuff that they had already done. But I also want to say that this new perspective answers some of the questions that seemed kind of mysterious at the beginning. So for example, these were some questions that you might have asked. Were the degrees of freedom living on the Planck brane here part of the boundary theory or the bulk theory? Can RT surfaces, the RT surfaces that we drew implicitly ended on the brane here? Can that really happen, that RT surfaces end on the brane? And there was this question, does the bath state really describe what's going on in the quantum extremal island here? And the answer to all of those questions is yes. In our framework, it's obvious. The brane is here in the middle of the geometry, the bulk geometry. And so, of course, the brane is part of the bulk description of this system. RT surfaces don't end on the brane. Rather, RT surfaces just wander through the bulk, and sometimes they cross over the brane to the other side. Again, entanglement wedge reconstruction says that the boundary state here in the blue region can tell me about what's going on in the middle of the ADS space, or in this case, can tell us what's going on in the brane, in the middle of the geometry in the Planck brane, in this region that we, has been dubbed the quantum extremal island. So in the setup that I gave you, none of these questions are really questions I would ask. The answer is obvious from what we know about ADS-CFT. To make this picture look a little bit more like the picture that our friends last August were looking at, what we do is we do a Z2 orbifold across the brane. Now I've thrown away half of my bulk, and this appears at the edge of the picture. But we still understand that it was inherited. All of that physics got inherited from this geometry here. And so these questions now have the same answers. And in particular, the ending on the brane is just an artifact of the Z2 orbifold and the fact that the surfaces could cross the brane in the covering space. Some other picture or questions we might think about is, was 2 dimensions important? Well, no, they weren't, because I just showed you a construction where this happens in any number of dimensions or can be extended to D dimensions. Was JT gravity important? No. Well, again, for D greater than or equal to 3, my setup was essentially Einstein gravity plus small higher curvature correction. Was the ensemble average of SYK important? Again, the answer is no, because, that was obvious. I'm just using the standard rules of ADS-CFT. I'm running out of time, but I'll just say there was also in this paper in the fall, there was this distinction between the full quantum description and a semi-classical description. And how does that arise in our picture? Well, we had these three pictures, but they're not all on the same footing as describing the physics. In particular, ADS-CFT says these two pictures are equivalent, they're identical, and I would say they describe a UV complete, or they provide a UV complete description. And so this would be what Maldacena and friends call the full quantum description of the radiation. On the other hand, in this picture, where I'm using Randall-Sundrum gravity, I know that that picture comes as an effective low energy description. There's a cutoff in the theory above which I can't use this gravity coupled to CFT description. There are also other features that are well, clearly not present in this description. And so this is the picture, this gravity picture that I'm doing is really the semi-classical description that these folks talk about. I've really run out of time, and I'll just say there are other interesting things one can talk about, but I won't. I'll just say that I think that this is a really dramatic new discovery, you know, the reproducing the page curve, you know, that points towards unitary time evolution. You know, I answered some questions with our D-dimensional construction, but there are lots of other questions that one might still want to ask and answer. And so I'll just end by saying there's lots to explore, and thank you for your attention.
Thanks, Rob, for this very enlightening talk. So,
okay.
So for questioning, I can start with one. In
sure.
The understanding of these quantum extremal surfaces, the way that you describe things, it seems like there wasn't any curvature singularity, the way that we would sometimes think about black holes as.
Right.
So would that change anything? Make it harder for to get these quantum extremal surfaces?
No, in this holographic setup, I mean, well, okay, it's a next project to look at, but let's see if I can go back and find a picture. Where's my black hole? Well, we had black holes that look something like this. You know, even in 2 dimensions, there's not really a singularity there. If there is a singularity, it's where the dilaton diverges, which is sort of a vertical line here. But you can also you know, we looked at a very particular case because of its simplicity, where the background geometry was just ADS, you know, empty ADS in D+1 dimensions. But you can very easily, you know, detune the temperature, and then what you have are hyperbolic black holes with a, you know, with a different temperature, but they have a structure where there's actually a singularity that runs across here. And you can do similar calculations, and it's really the, I mean, it's a little bit more challenging, but it's really the beauty of the geometry that, or the holographic entanglement entropy, that I'm doing a purely geometric calculation still. I don't really have to worry about, you know, quantum loops or planar diagrams in the CFT. But in principle, you know, it's no harder to calculate the quantum extremal surfaces, which is basically where my RT surface crosses the brane.
Thank you.
Okay.
There's a question from Shudipto. Shudipto, you can go ahead.
If I can ask 2 questions. So one,
sure.
Regarding that, while the resolution of the page curve is important,
yeah.
but there could be a general question that what is the end stage of this evaporation?
Mm-hmm.
Should I understand? It's a related question. Since the page graph flattened, is it possible to give a kind of remnant interpretation to what remains at the end of the evaporation?
Well, in the construction that we were doing here, it's not that the black hole evaporated. The boundary or the bath was at a finite temperature that matched the black hole temperature, and so Hawking radiation was leaking out, but an equal flux of bath radiation or thermal radiation was falling into the black hole. And so there was no real evaporation in that there wasn't a change in the background geometry. This black hole just remained the same black hole, or the background geometry remained the same background geometry that it was before. Is that clear, or?
Yeah, okay, thanks.
Karan Fernandez, yes, please ask your question.
Yeah, hi, Rob. Yes,
Hi.
I'm just a little curious about this this construction in one sense. So when you have this brane, I just wonder if you're saying that instead of considering ensemble averages, I can talk about there being a vacuum state at early times. And if I consider the entanglement surface to be large enough, there's an excited state which it'll go into. And so, I mean, these are clearly not talking about two saddles in this picture, it looks like, right? Like in the transition from the state that you begin with, which is crossing across the horizon, is very distinct from the state which you have at the end in the right-hand side. So, I mean, these are not two saddles of the full theory. There's like a brane in the middle which is waiting for you to reach there, and then when you arrive there, it's like, okay.
Yeah, when I say saddles, it's in the sense of, if I'm doing, well, in this calculation, when I say saddles, what I mean are there are two different saddle points or two different candidates for the extremal surface that I would choose. And so it's a competition between this saddle or that surface and that surface. And so that's what the two saddles are. If you were describing it in terms, I mean, what you might want to do, which is the way that, often the discussion is described in terms of, replica wormholes. What you're doing there is you're doing a calculation in a Euclidean quantum gravity path integral, and you're asking, which is the solution that properly describes the entanglement entropy in one phase or the other, and there would be different there'd be different solutions of the Euclidean gravity theory that would be relevant here and here. But so I'm not sure if I'm answering the question, but it's sort of, when I say that there's a competition or when I say there's saddles, it's not describing the time evolution of this system. I mean, there's one system and it evolves in time, but it's when I calculate the entanglement entropy, I rely on various tricks. In particular, I can rely on holographic entanglement entropy, or I can rely on a Euclidean path integral in gravity. And it's in those calculations that there's a competition between saddles. Did that make sense?
Yeah, I guess so. I mean, I'm just curious about, like, I mean, so you're essentially saying then that the saddle interpretation which we have in the island prescription is not essential to the result. I mean, that's what we're getting at. it sounds.
Yeah, I mean, it's really, well, yeah, that was actually part of the discussion here that I skipped over. I mean, you know, when Hawking originally discovered, well, when Bekenstein originally discovered black hole entropy, he was making qualitative arguments. But when Hawking really gave us a quantitative answer, A over 4G, what he did is he was looking at a saddle in the Euclidean path integral, and he was doing manipulations of that saddle, and it said that there was an entropy. It didn't tell us anything about, the microskates of, that were going into that entropy or anything like that. And so the surprise here is really that, we thought that to understand this other part of the page curve where the entropy is going down, that we would really have to, come to grips with a detailed understanding of the microstates and how the information gets encoded in the Hawking radiation. But the surprise is, no, there isn't. There's another, we do another calculation in Euclidean path integral, and there's another smooth saddle somewhere, and it tells us that, the entropy is actually going down, and so it's really, when we talk about these saddles, they're sort of crutches, but there's all sorts of that. They're tricks that appear in some calculation, but at the end of the day, there's all these microstates and information's being exchanged between quanta, and that's doesn't care about the saddles at all. It's just that the saddles somehow give us a very efficient or succinct story that encapsulate all of that complicated microphysics. Is that maybe a little bit closer to what you were?
Yes. Thank you.
Gautam.
Yeah, hi, Rob. That was a fantastic
Hi there.
talk. So I had one question. It's not directly related to probably the things that you focused on. It's about this ensemble interpretation of the quantum extremal islands. So the quantum extremal islands, can be related to wormholes and things like that. So what's your opinion on this fact that if you use quantum extremal surfaces, essentially your description of gravity is becoming like an ensemble thing and it's not unitary?
Well, I would say that my calculations today stand as a counterexample to that. I mean, I'm certainly not doing an ensemble. Well, okay, I'm not doing an ensemble average in my ADS CFT. I mean, certainly the description, the derivation of RT surfaces that go into this construction, they make. Well, not only do they make no reference to an ensemble average, they assume something quite contrary, where I am not doing an ensemble average. Now, so I just don't think that's somehow an essential feature of the quantum extremal islands. And I think for now, I'll just leave it there.
I see. Okay, all right.
I'm intrigued by all of the wormholes and the replica wormholes and the whole story that people are telling. But I mean, here's a calculation that gives me quantum extremal islands, but it has no sense of an ensemble average.
I see. So you're saying in a doubly holographic picture, this issue doesn't quite arise. Is that?
Yeah, in the description that we have here, you know, in this, in this picture, I'm just doing ordinary, well, it's actually, these two pictures are equivalent, and I'm just doing ordinary ADS CFT. And I'm not making any ensemble averages. On the other hand, when I talk about wormholes and all of that, or quantum extremal islands, I'm really talking about it in this third description. And I know that that's an effective description. And so maybe it comes from taking this description too seriously. I don't know. You know, in my picture, these two are, you know, what I call the UV complete framework. But this picture, that was really an effective picture that at least to a certain degree gave you an accurate description of the physics. But I know that it's not a complete description of the physics.
I see. That's very interesting. Okay, thanks a lot.
Okay. Well, yeah.
Are there any other urgent questions? Otherwise, we should move on and thank Rob for a wonderful talk. Okay, I don't see any other questions. So thank you very much, Rob.
Okay.